There we go. And I'll turn things over to group 645V.
All right, thank you. We're Team Speculos. We are, of course, group 645V. Our team is Adrian, Luke, myself, Joseph, Benjamin, Ethan, Nicholas, and Kellen. So on the agenda, we've got our Hedgehog Concept, product specifications, design features, product design progression, design analysis for each subsystem, and then the wind survivability tests. We have some videos there, the laser reflection targeting test, a couple more videos with that, cost breakdown, and then our product selection. So for our Hedgehog Concept, we decided to go with a low complexity product that has very few actually moving parts, some very easy, simple design as far as gearing, a low cost materials. So we have a lot of 3D printed parts and quite a few OTS parts as well. And then ease of manufacturing. So again, with the 3D printing, it's pretty simple to put it on the plate and have it print. And then ease of maintenance. So when it's out in the field, we believe it's an easy product to go out there and fix and maintain for years.
So our heliostat design has a reflective surface area of 108 square inches, which is double that of many other teams, with a weight of 4.6 pounds and a maximum height of 14.5 inches. Our design is well within the project constraints. Our heliostat is powered by two NEMA 17 stepper motors, which have a minimum step of 1.8 degrees. Thanks to a gear ratio of 4, we are able to get our heliostats step down to 0.45 degrees, and it is run by a Rhino brand AC/DC switching power supply. Again, the heliostat features a dual mirror design, which allows for increased reflectivity. All of the components have been either 3D printed or are off-the-shelf parts. Therefore, our design is cheaper, but can also be modified more quickly due to rapid prototyping. The output gears for the azimuthal and elevation axes are built into the structure itself, which minimizes chances of slippage and optimizes step resolution. The electrical components are within the box and can be accessed by simply unscrewing the lid and lifting the heliostat off. The gear ratio between the input and output gears is 4:1.
So in order to choose the design that we would base our first prototype on, we performed a house of quality analysis between designs from previous semesters, as well as the baseline design that was provided to us, and we compared the different characteristics of each design and how a customer needs, such as cost and ability to move and control the mirror's position, were met. We ended up choosing the design of Summer Group 3, which we preferred because we thought that the double mirror design and the two independently controlled axes controlled by belts and gears but the customer needs the best out of all the designs, especially in tracking the sun and having the most reflective surface area for its size. In addition, Summer Group 3's design was the easiest design to manufacture and prototype. This is what mainly set it apart from the baseline design, which performed equally well in the customer needs as a whole, but was much more difficult to manufacture. What we kept from the original design was the double mirror, the two independently controlled axes, a main support, and a cross support. But after starting the prototyping process, we removed the belts and replaced them with gears because those are much easier to custom manufacture for prototyping. We reduced the length of the supports to improve stability and also to be able to 3D print our prints since there's a limited 3D printing volume. And we also added larger L brackets to fit the new motors that we were given. The biggest change, however, was that all of our parts were now 3D printed, which made manufacturing and prototyping much easier since we can now custom make parts. After performing our wind test, we kept the major facets of our design, but we had to make some adjustments. We reduced the length of the main support and moved the electronics box to the bottom of the heliostat to improve the stability of the heliostat when it's exposed to the wind. We moved the azimuth motor to the control box, simplify the wiring, and reduce the tall metal parts. The final change that we made is that we added limit switches to our design so that when our control code was used to home the heliostats, the mirrors of the heliostat would hit the limit switches and the motor would stop turning.
This is the full assembly and exploded view. It is the left and right side. Pretty self-explanatory, but we'll let you guys digest it real quick.
All right, now we'll go ahead and start off by talking about our subsystems. So the first subsystem is the mirror array subsystem, which consists of two reflective surfaces to maximize the energy production. Now, the reflective surfaces are acrylic reflective panels, which are attached to 3D printed mirror panels, which is then attached to the cross support subassembly, which we'll see later on, through use of a sheet metal bracket that is screwed on and attached onto the cross support, which contributes to the lightweight and low cost design. And it is easily disassembled and assembled, so it definitely maximizes efficiency. And now we'll head more into our design analysis. So we took into consideration the 3D printed mirror panel, which has a 10% density infill. We calculated a max bearing force, which in turn we used to calculate the max wind force that the subsystem could withhold. And using that, we were able to determine that the maximum wind velocity that the subsystem can withstand is 134.5 miles per hour, which means it's more than capable to withstand any of the conditions that could be experienced in Las Vegas.
All right, so moving on to the support subsystem now. This subsystem features a few different components that comprise the main structure of the heliostat, including a box to house the electronics for the module that also acts as a support base. The box of the lid has a circular section that allows the main support for the mirrors to sit atop and also rotate about. The main support also has a mounting bracket on its side, which allows it to hold a stepper motor, which is used to actuate the cross support assembly. The cross support is fitted through a bushing in the main support, which allows the mirrors to rotate in the vertical plane. Now, in order to analyze the possible failure modes of the support structure, we considered failure due to bending at the base of the circular cross section. So the wind force on the mirrors due to average wind speed is 0.35 newtons, and the of inertia of the circular cross section is shown below. The resultant bending stress from this force is 4.78 kilopascals. And carrying out this same process for the maximum recorded wind speed in Las Vegas of 90 miles per hour, the bending stress is 0.45 megapascals, which is still well below the yield stress of the material used in the component, Hedg, which has a yield stress of 47.9 megapascals.
So another analysis we did was to determine the lift force on the heliostat, which is generated by the wind. This equation for the wind pressure P, it's an approximation used by civil engineers. The wind pressure can be multiplied by the area of the module to acquire wind force. And if we assume an angle of 45 degrees, a top wind speed of 35 miles per hour, and the given mirror area, we get a maximum vertical lift force of 2.352 pounds. The heliostat's total weight right now is 4.2 pounds. Therefore, it is not likely to be a mode of failure for our design. A wind speed of 46.77 miles per hour would be necessary to theoretically lift the heliostat.
Okay, now we come to the movement subsystem, which is used to position the mirrors relative to the target. In order to accomplish this, we used a set of NEMA 17 stepper motors, as previously mentioned. And again, as mentioned, we 3D printed a set of gears in a ratio of 4:1 in order to reduce the 1.8 degree minimum step of motors to 0.45 degrees rather. So in order to consider the possible failure of this system, we considered the possibility of having the wind force generated on the mirrors backdrive the motors, which would obviously cause them to be misaligned with the target. So again, with the average wind force of 0.35, we considered the worst possible case of no counterbalancing, or in other words, having all of the wind force acting on a single mirror to generate the maximum torque possible. With our design gear ratio, the effective torque that the mirrors are able to produce that the motors are able to produce in order to balance the mirrors is 1.8 Newton meters, which is more than enough to prevent the mirrors from backdriving. So they should be safe from being backdriven due to average wind speed.
So for our electronics that we chose to use for this project, we utilized an ESP32 rover control board. Now, this board allows for USB serial input, but it also allows for Wi-Fi implementation in the future. We're using two Pololu A4988 motor controllers, one for each of the azimuth and elevation motors. We have a Rhino PSB12-030-P switching power supply, which is a 12-volt AC to DC power supply and can supply 30 watts of power. Lastly, we have an SHTC3 temperature and humidity sensor, which is placed inside the controls and electronics housing box, which allows us to monitor temperatures inside of the box. These electronics allow us the capability of dual motor control to track the movements of the sun throughout the day. Our controls code is primarily written, it's completely written in the Arduino IDE environment. It's primarily written in the C++ language. It utilizes serial input sent to the ESP board by the user. So we set up our code to utilize custom functions based on the user input. And the functions that we created include homing, motor step and angular movements, set angle functions, control box temperature feedback, safe mode configuration, current position feedback, and power down mode. We also implemented an error correction ability for prototype testing and also for installation, which eliminates angular movement error due to poor installation, as well as gear backlash and gear meshing issues. The biggest threat to our electronics is the temperature inside the control housing. If that gets too hot, the electronics don't work properly. So what we did was we calculated the temperature rise inside the controls housing, and we found that by calculating the heat loss due to the inefficiencies within the electronics. And then we're able to create a ratio of watts per square feet of surface area inside the box. And using that ratio, we're able to determine that we have roughly a 23°F temperature rise under max utilization. Now, considering that the hottest temperature ever recorded in Las Vegas is 117 degrees Fahrenheit, that gives an enclosure temperature of 140. Now, 140 is quite a bit under the max operating temperature of the power supply, which is 167 degrees Fahrenheit. And that's the lowest among all of our electronics that we have.
So we had two tests to test our design, and the video playing right now is the low speed simulation where it would mimic regular wind speeds in Las Vegas and still be operable. And then the high speed one to the right that's playing right now is for when conditions say that it is unsafe for the heliostats to operate, and it would go into the safe mode seen there. And both of those tests passed. The next test was the laser reflection test. We had the laser simulating the sun, and we used our azimuth and elevation motors to get to certain angles along the wall, as seen in the video. We also had a passing code that could operate and reflect a laser.
All right, so under our cost breakdown, we were asked to produce a cost an estimate for a single unit production and then 3,000 unit production. So for our cost for fasteners, we had 8 unique fasteners that total for the single unit cost about $4.25. The total cost for OTS parts, which were primarily lab given parts, like our motors, limit switches, other parts like that, that came out to be $128.34. For our custom parts, which are primarily 3D printed parts, that was $53.08, and that was about 8 different parts. So for our total cost of assembly, we estimated about 2.5 hours to assemble our full unit, and it included our creating the supports, adding any fasteners, wiring up the breadboards and electronics, and mounting any motors and things like that. And we estimated that to be about $40.52 as far as assembly cost. So for our lab provided materials, that ran $128.11. And then our total cost of purchase parts was $57.55. So that single unit cost $226, which we believe is pretty low compared to most other products. And then looking at the 3,000 unit production run, we scaled that up to about $607,000. So we believe it's a pretty cheap unit to produce and then put out in the field. So we're going to go on to why our product is probably a better product than most. It's easy to manufacture and maintain. It's very few moving parts. It's easy to 3D print a whole bunch of custom parts as far as once you have the part files and things. It's cheap to produce on an individual scale and large scale as well. The large reflective surface area, we calculated that to be about $2 per square inch of cost. So for each square inch that we have a reflective surface, that's $2 it's going to run. It can withstand the asked for customer needs, the environment that it'll be in Las Vegas. And then it is effective in tracking the sun and being able to reflect any sunlight towards the central tower. And as well, we have a wide base and heavy unit that'll sit on the ground. And as we've shown in the analyses, it'll withstand the environment that it will be placed in. So thank you for joining. That's our presentation about Speculos. And if you have any questions, we'll field those now.
All right. Thank you for the presentation. Do we have questions from our panelists?
Yeah, so this is Rick Miles at Northrop Grumman, and I haven't asked this of other groups, but watching some of the aerospace presentations kind of triggered this thought in me. So you've got 220 whatever odd dollars for your prototype cost. So first on your cost slide, I would make sure when you show the prototype cost and the cost for 3,000 units, I would put both columns in the per unit cost so that you can see the reduction. I think that comes across as, you know, what sort of improvements you're making by going with a production run.
Okay.
But one of the things that I wanted to ask is, so if you're spending this much money for this heliostat farm, when do you expect to break even with your cost versus the amount of energy that you end up producing? It's one of those things, the more I listen to, you know, these solar collectors and that sort of thing, when is it that I expect to get my investment in putting out this heliostat farm that I'm all of a sudden going to break even and basically getting free energy?
So I would say that we have not thought about that. And I say that reluctantly just because we were tasked only with finding costs for the heliostat themselves. Now, if you go towards the efficiency of the actual central tower, that's where you're going to get your actual energy from. And I haven't looked into actual central towers and their efficiencies and cost, your cost per unit energy in that aspect. But as far as the array, this is a cost we've calculated, but I'm not sure when you're going to get your money back as far as your energy produced.
That's a fine answer. I didn't expect you to have the answer to that. It's just one of those head scratchers that I started thinking about listening to all these presentations. So in general, good presentation.
Thank you.
Okay. Any other questions from our panel?
So could you please change to page 11?
I apologize. Which page 11 you said?
Page 11. So I'm a layperson of this kind of things. So I'm just curious, the sigma yield times percent fill. What is the percent fill?
Since these parts are 3D printed, they're not 3D printed to be perfectly solid. So our infill and printing was about 10%.
Oh, okay. So the support subsystem, could you change, because there was no page number for that, those. Oh, okay. Next one. Next one. So this is the thing that I feel like, well, when you look at your design and you have a kind of feeling which are the weakest part and which are the part that will fail first. And I feel like you have big chunk of material for the support subsystem. And if you want to do structural analysis, this would be my least concern. It's really unlikely that big chunk of system will fail first. So it's really unnecessary to do analysis part. You probably need to focus on like the rotation part or the linkage component with mirror, that kind of thing will fail first because there was a hole there. They are much thinner, the stress concentration and everything. And also from your calculation, you can see that the maximum stress from your calculation is like 0.45 megapascal and your strength is 47. It also shows that this kind of structure analysis is really unnecessary. This is really unlikely to fail. So this is my feeling. So before you do the structure analysis, first check which component is a critical component, which point is a critical point, and then do the structure analysis there. Or if you have several options, you really don't know which one is the weakest part, just check the zero point. But from what I can see of your structure, the big chunk of the support system is really unlikely to fail. That's my feeling.
Yes. Sorry, yes. And we did consider more likely modes of failure as we showed in later slides. This was just to ensure that
yeah,
section would be secure, which yes, you're correct. It obviously is of least concern for that.
Yeah. And could you please go back to the page 11? I think I have something else on page 11. So the first 38.6 is based on the material and the of your actual design, right?
Yes, that's correct.
Okay, and you use that one to calculate the max wind you can the max F wind max is 12.28.
Correct.
So what is the requirement of the maximum speed? Like, I don't know. So right now your calculated result is 134. It can withstand 134. What is the requirement?
Well, we have basically for our module, the probably mode of failure that we're most concerned about is the possibility of having the gears back driven due to the torque exerted by the wind force. And this caps out about gusts of roughly 45 miles per hour. So once we start experiencing gusts of around 35 to 40 miles per hour, which is typically, when higher winds will start to be detected by our system, our code will tell our module to go into the safety position. Yes, and so that's more
okay. Thank you. So that all my question. Overall, great job. Thank you.
Thank you.
All right. This has become more of a tradition than anything else. Since you guys are the last group, I have to ask. So the ultimate application for this thing is, when Sheffy gets his final solar field, is basically to reduce or reverse entropy, right? He's taking products of combustion and basically breaking them down into really the goal is to make fossil fuel out of carbon dioxide. So there's a big entropy reversing process involved at kind of the application scale of this thing. Do you guys have a sense of how much entropy your system is going to be generating?
I don't think that was thought of in our design. We don't really have an estimate on how much entropy our system will create. But I would say based on having 2 mirrors and more energy reflected, it'd probably be a little bit more than a single mirror unit or such, you know. So I would say there's probably a little bit more entropy than most. So if lower entropy is not wanted, then we might want to go back to the drawing board on that.
Oh, no, it's a very theoretical sort of esoteric question. There's, at least for this application, almost no concern, at least that I would be aware of for how much entropy is being generated. It's just an interesting question because ultimately you guys are, like I said, you're creating a region in space ultimately where entropy is being reversed. Right. And it's not really fair to say that because entropy is being created somewhere else in the universe to offset the entropy that you're reducing at the focal point. Otherwise, we wouldn't have the second law of thermo. But you guys are like the conduit for that. Right. And so it's just an interesting kind of thought experiment. How much entropy are you producing at the point where you're concentrating the sunlight? So anyway, I thought I would ask, but and there is actually a way to calculate it. And if you guys jump back into the second law chapter of your thermo textbook, you might find it in there. But anyway, thought I would ask. Mostly for tradition's sake, because I asked this of every group at the end of the semester. So anyway, okay, you guys are off the hook because we're at 5:15. So anyway, let me stop recording